Well, hello. It's time for some calorimetry problems. We'll start with number 21 from chapter 19. This problem is about taking some copper pellets out of a very hot oven, a 300-degree-Celsius oven. That's hotter than a pizza oven, because if you convert that into Fahrenheit, I'm assuming it's, well, okay, fine, let's do it real quick. 300, multiply that by 9/5, and then add 32. Okay, it's about the temperature of a pizza oven. Take those copper pellets out of the oven and dunk them into a small quantity of room temperature water, 20 degrees Celsius. They tell us that the volume of water is 100 milliliters. A very useful number to remember is the average density or usual density of water. It's 1 gram for every cubic centimeter. That's the easiest possible density to remember. And that's no coincidence, right? The milliliter is actually defined as the volume of 1 gram of water. Yeah, I meant to say that 1 milliliter, that's a unit of volume. That's the same as a cubic centimeter. Here's a little cubic centimeter, also known as 1 milliliter. So 100 milliliters of water has a mass of 100 grams. That's very easy. Off to the side, we're going to need the specific heats of these two substances. This number worth memorizing because you see it so often. It takes over 4,000 joules to raise 1 kilogram of water by 1 Kelvin. It only takes 385 joules to raise 1 kilogram of copper by 1 degree Kelvin. So you could say that water has more thermal inertia. You're going to have to dump a lot more heat into water in order to change its temperature. And what we're supposed to do is just find the temperature at which these two meet in the middle. Obviously, the copper pellets are going to cool down. The water is going to heat up. Whatever heat is given up by the copper will be absorbed by the water. We're not going to worry about any exchange of heat between the copper and the styrofoam cup because styrofoam is a really good insulator, and it would actually take a while for the styrofoam to absorb any significant amount of heat. So the thinking is that the water and the copper finish exchanging heat and reaching equilibrium before either of them have a chance to exchange heat with the with the styrofoam or with the air or the surroundings. So one possibility is that these are so darn hot that they actually raise the temperature of the water all the way up to 100 degrees. Because remember, this temperature is way up at 300, and heat always flows from a higher temperature to a lower temperature. So this temperature could be dropping, and still be higher than 100 degrees. It's possible that all of this water could even boil. So use your common sense. I mean, we don't have a whole lot of experience in everyday life with dropping copper pellets into water, but 100 grams of water and only 30 grams of copper, plus look at the difference in the heat capacities. It seems to me that we're just not going to have enough heat to dump into the water to raise its temperature all the way to 100. So I expect the temperature to be somewhere in the middle. And in order to get a sense of what this might look like, why don't we check a video from YouTube? So here's a guy who's heated up a cannonball until it's red hot, and he's about to dump it into water and ice. And I read in the comments that this was common practice hundreds of years ago in warfare. People would launch cannonballs at each other's ships that were red hot. That way, when they struck the ship, they light it on fire. Water, set it on. So that's something you observe in everyday life. It's a little different than the problem we're looking at. That's what happens to cannonball. It's much hotter than even if you do it. You can see it's already boiling in the water. Now that's enough that. Maybe some more you can get that up. The approach to calorimetry problems, the problem setup, very simple, very straightforward. Consider the situation we just looked at. We had a styrofoam cup, copper pellets, and water. Those are three different bodies, different substances that are possibly at different temperatures, although the styrofoam is probably at the same temperature as the water, room temperature. And in general, those three bodies will all exchange heat with one another. So if this is the copper and this is the water, they may be exchanging heat with one another. These arrows are probably a little misleading because remember that the heat always flows from the hotter body to the colder body. So there should really only be one arrow. I'm just leaving the options open because it depends on the various temperatures. And if you've accounted for all the bodies in your system, the idea is there's no heat flowing in from the outside. And of course, in real life, some of the heat of that water copper system would be flowing into the air, but that process happens so slowly compared to the exchange between the copper and the water that we could just disregard it over the time scale of the water and the copper reaching equilibrium. So we assume that the net heat into the system would be zero. So there may be heat exchanged within the system, but not between the system and its surroundings. Now, the convention in your book, and I like the way your book does this, Q is a signed quantity. It can be positive or negative. So if overall heat is leaving body 3, like if we're talking about the copper, for instance, because remember, it may be giving up heat to number 2, but it could be receiving heat from number 1. When you account for both of those, if you find that there's a net loss of heat flowing out of body 3, then Q3 would be a negative number. So if heat is flowing out of a body, Q is negative. If heat is overall flowing into the body, Q is positive. And that's why the sum of these three quantities could actually be 0. Of course, some of them, one of these quantities or one or more would have to be negative if they sum to 0. That's it. This is how you solve calorimetry problems. It's as simple as that. Now, if there are no phase changes within the problem, if we don't have to worry about the water boiling or freezing or anything else boiling or freezing, then we're really only using this expression for heat. If the only effect of the heat is to change the temperature but not change the phase, you can use MCAT. This is the specific heat. This is the mass in kilograms. And this would be the temperature difference in Celsius or Kelvins, same thing. Now later we'll talk about heat exchanged with gases, and this would be the molar specific heat. So this would be number of moles N instead of mass M. Okay, that's the approach that we'll use. In this problem, it's actually a little simpler. There's only 2 bodies that we have to worry about because, again, we're going to pretend that the styrofoam has such low thermal conductivity that there's no exchange of heat between the 2. Okay, the whole point here is to find T final. So what I'll do is set up the math, and then I think I'll do a spreadsheet. We don't need a spreadsheet to solve this problem. It actually doesn't make solving the problem any easier for this particular problem, but it would be nice to help us visualize what's going on. But we'll start with this. The heat given up or absorbed by the copper plus the heat given up or absorbed by the water, the sum of those 2 has to equal 0. Whatever the copper gives up, the water absorbs. So that's simple to conceptualize when you only have two bodies in your system. Mass of the copper times the specific heat of the copper times delta T for the copper. Well, that would be the unknown final temperature minus initial temperature for the copper plus mass of the water, specific heat of the water times final temperature minus initial temperature of the water. That's got to equal 0. And when you first look at that equation, there appear to be a whole bunch of different quantities, but usually you know the masses. I shouldn't say usually because it really depends on the problem. But in this case, we do know the masses. We know the specific heats. We know the initial temperatures. The copper is 300 degrees Celsius. The water is 20. And there's only one unknown because the nice thing is, the whole point is that they have the same final temperature. We don't have to specify final temperature for the copper, final temperature for the water. The idea is that these 2 bodies have reached thermal equilibrium. They're at the same temperature. They will always meet in the middle, so to speak. Heat flows from the hotter object to the colder object until the 2 temperatures are equal. So this is just an algebra problem. Honestly, is this problem even worthy of 3C? This is a calculus-based class with the focus on modern physics. but we do have to cover it. We'll get into some more difficult problems in a little while, but this is a problem that could have appeared probably in a high school class. All right, let's do the algebra. I'm going to collect everything that has a T final on one side, so it looks to me like we've got T final times mass of the copper, that's supposed to be lowercase c, specific heat of the copper, plus mass of H2O, specific heat of H2O, and then all the other garbage I'm going to move to the other side. So that looks like it's going to be mass copper, specific heat copper, T initial copper, plus mass H2O. Maybe I should just put the whole thing in parentheses and written the subscript once. That would probably be easier. Okay. I think I'll do that now. Now, you might be wondering, hey, wait a minute, do we need to convert this into kelvins? Because I don't see a difference here. The rule is, if you're just talking about temperature differences, you don't need to convert because the 273 constant would just subtract. Well, here I don't see a difference. I only see T final. That's true, but in the first equation, it was a difference. So it's okay to leave it in Celsius. There is no need to convert into kelvins. Okay, so you know what I'll do is I'll say MC T initial for copper plus MC T initial for water, and then we divide the whole thing by MC for copper and MC for water. That's about as compact as I can make that. Could I have guessed this equation without doing the math? I don't think so. I don't see any shortcut to get there. And now we just plug in numbers. It's kind of fun to guess ahead of time what you think the temperature would be. We know it has to be somewhere between room temperature, 20 degrees, and the 300 degrees of the copper. So which will it be closer to? Okay, and I have to pause to think about this for a moment. It's actually pretty easy to answer that question. What I've done here is solve for temperature change for just one of the bodies in terms of the heat that it absorbs or gives up divided by MC. And we can see here from the denominator, because remember, Q is going to be the same in absolute value for the copper and the water. The heat given up by one is equal to the heat absorbed by the other. So this doesn't change. Let's just look at the denominator. If you make M smaller and C smaller, delta G comes out bigger. Well, look at copper. Copper's mass in this case is quite a bit less than water's mass, and its specific heat is less than 1/10 that of the specific heat of water. So that tells me that the temperature change is going to be a lot bigger for the copper. The copper's temperature will come way down. The water's temperature isn't going to change by much because remember, water has a lot of thermal inertia, if you want to think about it this way. So I expect the temperature to be considerably closer to 20 degrees than it will be to 300 degrees. And I'll pause while I plug in these numbers. Maybe you should do the same. Or you know what? Maybe I'll give you some tips on using your calculator efficiently. You probably don't need these tips from me, but what I'm going to do is calculate the numerator first because it's more complicated. See, there's an MCT for each, and I'll put that into memory. So also, here's another observation. Do you see how we've got mass on top and bottom to the same degree, mass to the first power? I don't actually need to convert from grams into kilograms. So I'm just going to stick with grams. For the copper, I've got 30 grams times the initial temperature of 300 times the heat capacity, that was in the middle there, MC, heat capacity of 385, plus for the water, we've got a mass of 100 times the heat capacity of 4190 plus the initial temperature of 20 equals, okay, I'm going to put all that into memory, shift memory input, and you know, I am being a little daring here with my mixed units. The safest thing would be to just use SI throughout, but if you've got some practice knowing when and when you can and cannot use mixed units, then go for it. Okay, now I will do the denominator. 30 grams of copper times the heat capacity of 385 plus the 100 grams times the 4190 equals, now I'm going to take the reciprocal to put that in the denominator. All right, there's that, and then I multiply by what I have in memory. and I'm hoping that I get a number close to 20 degrees. Nope, I got 9 degrees. I obviously did something wrong with my calculator. I'll pause and redo this. Okay, I got it right the second time. I find that the final temperature, I'll just put it here, should be 27.5 Celsius degrees, or degrees Celsius, I should say. Not to be pedantic here. Okay, that's supposed to be a 7. Just as we expected, it's a lot closer to the temperature of water. So the water temperature didn't rise by much. Now what I'll do is open up Excel, and let's look at some of this process in a spreadsheet. Okay, I just got confused about pausing. I don't know when I stopped the recording, so let's hope I didn't cut out a big chunk here. What was I doing? I had to redo my calculation of this quantity, and I found that the temperature final that's supposed to be a 7, 27.5 degrees Celsius. So as expected, the temperature at which they met in the middle is quite a bit closer. It's not really in the middle, is it? It's much closer to the initial temperature of the water. It's very difficult to raise water's temperature compared to the temperature of most metals. Okay, so the algebra is easy, but let's take a look at what's going on using a spreadsheet now. I've made a very crude spreadsheet here just to investigate the heat entering and leaving the copper and the water. And I actually want to add some space here. Okay. Let me just enter the values that we were given. And typically what I'd want to do is include the units here. I'd want to make sure that the viewer knows that the mass of the copper is specified in grams. But since we're watching an instructional video here, I'll just point out now that I'm talking about, well, I'll do everything in SI units. That's the safest thing. The copper's mass was 30 grams. That's 0.030 kilograms. And the heat capacity we were told is 385, or you could look that up. 385 joules per kilogram per Kelvin. The initial temperature was 300 degrees. Of course, that's not really SI units, because I guess, if anything, SI would be the absolute scale. But you know that I'm talking about Celsius degrees. The mass of the water was 100. Heat capacity is 4190. And the initial temperature was room temperature. Okay. Here's where I'm going to enter MC delta T, MCAT, for each of these. And I'm not actually using Excel to solve for the final temperature. We already did that. I'm going to just pick a temperature. I guess what I can do is enter the final temperature that we already calculated. So here I'm going to enter the formula. This would equal the mass of the copper times the heat capacity or specific heat of the copper times final temperature minus the initial temperature of the copper. Oops. Oh, come on, Excel. Just leave me be. Let me do my thing. I know what I'm doing here. Okay, I didn't actually enter a final temperature yet, so this number is not accurate. Over here, the heat given up or absorbed by the water would be the mass of the water. Hang on a second. I did that in grams, didn't I? Okay, this should be 0.10. Have to divide by 1,000. .100, fine. Okay, so the heat given up or absorbed here would be mass of the water times specific heat of the water times the common final temperature minus the initial temperature of the water. And let me change the display option here to show the appropriate number of significant digits. There's that 100 grams. Same thing here. That's a nice practice to observe when you're making spreadsheets. Okay, well, this isn't right, is it? Because the heats are unequal in absolute value, and that's because I haven't actually entered the final temperature. What did we find? 27.5? And there it is. There's some rounding error, of course. Let's see, did I write down? No, I checked my calculator to see if I still had the number up so I could put in some more digits. But close enough. We can see that the copper gives up about 3 kilojoules, 3.1 kilojoules of heat or energy, thermal energy, and the water absorbs those 3.1 kilojoules. So we didn't need the spreadsheet for this problem, but it's kind of nice to actually look at the numbers and compute those efficiently. Of course, we could change the masses here for a different problem. But an Excel spreadsheet will be more useful in other problems from this chapter. I find this next problem rather interesting. It touches on a major theme in the physical sciences and I guess measurement sciences, or measurement science, which is that it's nearly impossible to measure something without changing, to some extent, the thing that you're measuring. In this problem, we're trying to measure the temperature of a beaker of water, and the act of plunging the thermometer into the water will tend to lower the temperature of the water a bit. So the thing that you were trying to measure is changed by the act of measurement. And the further you go in physical sciences, especially in quantum mechanics, the more you discover that's unavoidable. There's really nothing that you can measure without changing it at least a little bit. Now, on the macroscopic scale in a laboratory, you can all but eliminate those effects. But when you get down to the level of the atom, it's truly impossible to circumvent that difficulty. If you took 3B, you may have studied voltmeters and ammeters. And when you measure the voltage of something, you have to put a probe across the thing that you're measuring. And that probe provides another path for current to flow. And so you've already changed the thing that you're trying to measure. Anyway, the details of this problem are thus. We're told that the thermometer, which is mostly glass, would have a specific heat basically equal to that of glass. Yes, there's a fluid within it like mercury or alcohol, but we can assume that has a very low specific heat compared to the glass. And not just a low specific heat, but a low heat capacity, because specific means per kilogram, but there's very little alcohol in that immersion thermometer. So, if you take the specific heat that's per kilogram and multiply by how many kilograms you're talking about, you may end up with a considerably lower actual heat capacity if you've got much less than 1 kilogram. Okay, we're told that after taking this room temperature thermometer, the thermometer is sitting on a table, it reads 20 degrees, you plunge it into the beaker of water, there's 200 milliliters of water, and the alcohol within the immersion thermometer expands, and the new reading on the thermometer is 71.2. So we know that the water started out definitely warmer than the thermometer, and the two met somewhere in between. This was their in-between temperature. So the initial temperature of the water must have been a little bit higher than this, because we know that the water's temperature will come down a little bit, the thermometer's temperature will go up quite a bit, and they'll meet at some temperature in between. This is the temperature in between. So the whole point here is to find the actual temperature of the water beforehand. Now, anytime you've used a thermometer in the kitchen or to measure your temperature, I seriously doubt that you did this calculation, but if you needed that kind of precision, I suppose you could. And since this is the calorimetry problem, it's the same starting point that we used in the previous problem. We say that the heat, I would say the heat absorbed by the thermometer plus the heat given up by the water, that would have to equal 0. And I'm being a little imprecise with my language, because when I say heat given up, it sounds like I'm talking about absolute value. And when I say heat absorbed, it sounds like I'm talking about absolute value. But I really just mean the sum of the heats is 0. One of these will have to be negative. The body that gives up heat is going to have the Q that's negative. The water has to give up just a little bit of heat in order to raise the temperature of the thermometer. Now, think about this for a moment. An ideal thermometer, a thermometer that doesn't change the temperature of the thing you're measuring at all. What kind of heat capacity should it have? A very high heat capacity or a very low heat capacity? Well, think about it. The two of these have to reach a common temperature. And that means that the thermometer's temperature is going to have to change at least a little bit. Now, if the thermometer had an extremely high heat capacity, then you would have to dump a lot of heat into the thermometer in order to get it to that final temperature. But that heat comes from the thing you're measuring. And you don't want to take heat from the thing you're measuring because you don't want to change its temperature. So an ideal thermometer, a perfect thermometer, would have a very low heat capacity, basically a heat capacity of 0. Well, this is not a heat capacity of 0. It's not a specific heat of 0, but remember, this is per kilogram. If you were to multiply this by the actual mass of the thermometer in kilograms, you would get a very low heat capacity, and that means it's not going to draw a whole lot of heat off of the water in order to reach its final equilibrium temperature. So we expect there to be a fairly small effect. Okay, the rest is just gravy, right? We say mass of the thermometer, and I didn't write that down. Let me put that over here. This is 50 grams. The mass of the thermometer is only 50 grams. And we know the mass of water, that's easy, it's 200 grams. Specific heat of the thermometer times T final minus T initial for the thermometer plus the mass of the water, specific heat of the water. I'm going with W this time instead of H2O because that's easier, times the final temperature minus the initial temperature of the water. The sum of those has to be equal to 0. And this problem is a little different from the previous problem. Here, we actually know the final temperature. The thing that we're evaluating is the initial temperature of the water. That's what you're really trying to measure. It better be close to this number, otherwise the thermometer is useless. What if the initial temperature of the water is calculated to be 90 degrees? If the water was 90 degrees before you stuck the thermometer in, and now the thermometer says 71 degrees, then it's completely inaccurate. It would be useless as a measuring device. So we're hoping that this number comes out pretty close to what the thermometer gives. Okay, let's solve for T initial of the water. And I'll just do this all in one step. Here's what I find. What can I factor out here? I could factor out a T final. I've got MTCT plus M water, heat capacity of the water. What else do I have here? Minus MC or MT CT T initial of the thermometer, and I would have to divide all that by. Okay, so you can check my algebra. I believe I did that correctly. I'm taking a quick glance at the book to see if they have a similar formula, and they did not do the algebra. Okay, so I'm just going to plow ahead here and enter this into the calculator. I managed to get it right the first time for this problem. I find that the water's initial temperature was 73.5 degrees Celsius, not the thermometer reading of 71.2. So whatever heat was given up by the water in order to raise the thermometer's temperature to this final temperature, that heat was enough to drop the water's temperature from 73.5 to 71.2. So again, we see that the water's temperature changed only by a couple degrees, whereas the thermometer's temperature changed by a whopping 51.2 degrees. They exchanged equal amounts of heat because there's only two bodies in this instance, but one of them had a much larger temperature change. Again, I'm just using, or you can see that by using this relationship, capital M. For a given amount of heat, the smaller the mass and the smaller the heat capacity, specific heat, the larger the change in temperature. And the thermometer definitely had a smaller mass than the water, 50 grams instead of 200, and it had a considerably smaller specific heat as well. So it's no wonder that its temperature change was much more. That's the whole point of a thermometer. It's supposed to just adopt whatever temperature is held by the object that whose temperature you're measuring. That was a clumsy sentence. Let's take another look at this problem using a spreadsheet now. Okay, now since this is a two-body problem, just like the previous one, I can actually adapt my previous spreadsheet to this problem. So I've changed the subscripts from copper and water to capital T for thermometer and W for water. And this time we have a different set of unknowns and knowns than we did in the previous problem. The mass of the thermometer was given as 50 grams. That's 50 thousandths of a kilogram. The specific heat, that's the heat capacity per kilogram, we were told is 750. That's in SI units. And we're also told that the initial temperature of the thermometer was 20 degrees Celsius, room temperature. We're dealing with 200 milliliters, that's 200 grams of water. Same heat capacity or specific heat as before. This is what we don't know now. In the previous problem, we knew this number. Now this is what we're looking for. So I'm going to leave that blank for now. And what I'll do instead is first calculate, let me also add, we were told that once the thermometer has reached equilibrium with the water, the temperature that it reads, which is the temperature of the system, 71.2. Okay, so we know the final temperature. And that means I can calculate the heat absorbed by the thermometer. I'm just going to use MCAT, MC delta T. So this equals mass of the thermometer times specific heat of the thermometer times the known final temperature of the system minus the known initial temperature of the thermometer. Okay, so it came out positive, which means heat did enter the thermometer, 1.9 kilojoules to be more precise. And I'm going to make the assumption now that the water gave up an equal amount of heat. Now, when I say it gave up an amount, that would be an absolute value, but to reflect the fact that the heat left the water, I use a minus sign. So I'm going to say this equals the negative of that. Okay, and now that I know the heat given up by the water, I can figure out what its initial temperature is. So look back at your, in fact, maybe I'll pause and do this on paper. Hang on a second. This is the relationship between heat, mass, specific heat, and the initial and final temperatures. Let's solve this for T initial. That's what we're interested in. It looks to me like I would have, okay, hang on a second. T initial equals, let's see, I'd have to do TF minus MC over Q. Did I do that right? Let me check that. Of course, I didn't do it right. That's a little embarrassing. I couldn't do a two-step algebra problem in my head. But hey, that's why we have algebra. I don't think I've gone on the spiel in this class, but to me, algebra, we have algebra as a species because our short-term memory is limited. You know, if you say something like, hey, I'm thinking of a number, I squared it, and I add 2, and I get 11. What's that number? Most of you know 3 because you square it, you get 9, add 2, that's 11. But as soon as you add, 3 or 4 more steps in there, you can't do it all in your head. So you have to write it down and manipulate everything step by step. That's algebra. If we had evolved to have 100 times the storage capacity in our short-term memory, who knows if we would even need algebra, maybe only for the most challenging of problems. Okay, so that's the formula that I'll implement in the spreadsheet here. I go over to the cell for initial temperature of the water, and I say that's equal to the final temperature minus the heat for the water, and that is a negative quantity, divided by, now I could put parentheses and put MC, but I'm going to do divided by M divided by C. So divide by mass of the water, divide by specific heat. Ooh, and now I'm realizing, do I have to use SI units? Well, that's okay because my spreadsheet uses SI anyway, so I'm not going to worry about grams versus, no, I have to, look, I entered 200 again. I did that wrong. Okay, so let me finish the formula first. And when I hit equals, I don't think it's going to come out right. Yeah, see that? 71.2. That's practically the same. We already know what the answer is. I got to fix this here. This is 200 thousandths of a kilogram. All right, and there's the answer that we already solved for. So it's kind of nice to solve the problem using a spreadsheet, look at things a different way. Problem number 25, peanut butter mouth there, is yet another problem involving dropping a piece of hot metal into 200 milliliters of water. Whoever wrote these problems really likes that number 200 milliliters. Remember, for water, it's very easy. 1 milliliter, that's the same as 1 cubic centimeter. That is the same as 1 gram. And the metal that we're talking about in this instance is iron. And over here, I will quote the density of iron. You can look that up in a table. It's in your book somewhere, or you can Google it. If you're doing problems for this book, it's probably safest to use the value in the book, but that's given to us as 7870 kilograms per cubic meter. Remember, water is 1,000. So this is almost 8 times as dense as water. We know that, right? Iron is very dense. Did you know that when you pick up a microwave oven, first of all, it's kind of lopsided with the weight. The weight feels like it's all on one side, and that's because almost the entire weight of that appliance is the transformer, which is, I don't know, it practically fits in the palm of your hand. That transformer is a bunch of copper coils wrapped around an iron core. That's almost all the weight. If you ever have an old microwave oven that you're ready to throw out, take it apart first. Check out the transformer. You know what? You should probably let it sit for a few days before you take it apart, because there's a capacitor in there. And unless you know how to discharge that, you might shock yourself, and it could be injurious. Okay, the difference between this problem and the other problem about dropping metal into water is this metal is much hotter. Instead of 300 degrees, we're way up at 800 degrees Celsius. This is a lot more like that YouTube clip. We might expect this piece of metal to be glowing hot. I don't really know about that. If it's going to be glowing red, it's probably not quite hot enough for that. But we can expect it to boil some of this water. At that temperature, it should have enough heat, thermal energy, to raise the temperature of water all the way to boiling, and then to convert some of that into steam. See my steam coming off here? Okay, one thing we need to do is figure out how much mass is in these 65 milliliters of iron. We know the density, but we need to know how to convert this into cubic meters. So 1 cubic centimeter, well, a centimeter is 100th of a meter, and we're cubing that. That's a 3 right there. So there it is, 1/1,000,000th of a cubic meter. Okay, so the mass of the iron here would be 7870 kilograms for every cubic meter, and we're dealing with 65 millionths of a cubic meter. Let's plop that into the little handheld computer here. And I find that we're talking about 512 basically grams. Of course, I'll convert that into kilograms when it's time to plug it into the equations, if necessary. And the added complication here is the phase change, but the basic approach remains the same. The song remains the same. We just say that the heat given up by the iron plus the heat given up or absorbed by the water should equal 0 if this is a closed system. Yes, it's true that the water is going to be exchanging some heat with the surroundings, but you know, in a carefully controlled lab experiment, you'd want to minimize that. Have a styrofoam container, have a lid on it perhaps, but most of the exchange is happening between the iron and the water. Okay, so that we're assuming that everything else has been controlled or accounted for. Okay, well, this is the part that has 2 contributions now. Let's see, can I come up with some abbreviations to use for the spreadsheet? Yeah, I'm going to say that this has 2 parts. There's the heat for the water associated with the rise in temperature. First, we have to get the water up to 100 degrees. Then we have to boil it. And you've seen that already. What do I call this? I'll say the heat for the water associated with the vaporization. Remember that latent heat of vaporization? This is just my notation for this problem. This is Q sub W, comma, L sub V. I guess this looks like a subscript for a subscript, but hopefully you get the idea. We need heat to raise the temperature of the water, and we need heat to boil the water. And the sum of all those has to be 0. All right? And the rest of it should be easy. Mass of iron, specific heat of iron, T final minus T initial of the iron. Again, I don't have to distinguish all the different T finals because they're all the same. The system reaches equilibrium. There's only one common final temperature. Okay, for the water, mass of the water, specific heat of water, T final minus T initial for the water. And lastly, the simplest formula, you just take the number of joules required to boil 1 kilogram of water and then multiply by how many kilograms you have. So mass of the water. Now here's where I like what your solutions manual did. It's not likely that all of the water gets boiled, only some of the water gets boiled. So let's use this symbol, M sub S. I think the S is for steam. This is the quantity of mass of water that's actually boiled. That many kilograms times the latent heat or heat of vaporization for water, and we set that equal to 0. What are we solving for? This quantity. We'd like to know how many kilograms are actually boiled. Now, we've only written one equation here, so we can only solve for this unknown if it's the only unknown. One equation can only have one unknown. So we go through here. Yeah, we just calculated that. That's the 512 grams. We looked that up in a table. I wrote that down here. The initial temperature we're given is 800 degrees Celsius. We know the water's mass, 200 grams, 4190. Now, what about the final temperatures? I think I skipped over that. The final temperatures. This is a very subtle point. Well, we've already talked about the fact that all of the water must be boiled before the steam can rise in temperature. When water undergoes a phase change from liquid to gas, presumably at atmospheric pressure, it gets up to 100 degrees Celsius, then it undergoes the phase change, and now you've got gaseous water or steam. That steam is not going to rise in temperature until all of the water has been boiled. And remember the reasoning, if the steam got hotter than that, if the steam was 101 degrees Celsius, it would now be hotter than the rest of the water, which means heat would immediately flow from the steam back into the water. So it can't have a temperature higher than the water that's still in liquid form. Okay, now if this thing was hot enough, you know, if we brought it in and dumped it at like 5,000 degrees Celsius, I think it would boil all the water and then superheat the steam. But that seems unlikely at this temperature. So I think we'll start out with the assumption that only part of the water boils, and then you've got steam at 100 degrees and water, which is still at 100 degrees. If we make that assumption and it's wrong, something funky is going to come out of the math, and that would probably alert us to the fact that we made the wrong assumption. Okay, now, the other point to examine is, how do we know what the final temperature of the iron is? Is it possible to boil all the water and have steam and water at 100 degrees and the iron has still not cooled down to 100? Like, what if the iron only cools down to 500 degrees Celsius and half of the water has been boiled? Well, think about that for a second. If the iron is still in contact with this liquid steam mixture, and that mixture is 100 degrees Celsius, while this is 500 degrees, heat flows from hot to cold. Wouldn't the iron still give up more heat and continue boiling it? Yes. So we have to assume that the iron is also at 100 degrees. If it was any hotter than that, it would still be boiling some of the water, and eventually it could be superheating the steam that remains. Okay, so there's really no unknowns here except for the mass of water that's actually boiled. We know that the final temperature has to be 100 degrees. So let me solve for M. And this algebra is trivial, right? The mass of steam would be, okay, negative mass specific heat minus mass specific heat delta T. And then we would just have to divide by the heat of vaporization for water. And I'm going to remind you about that value. I'm just taking it from the book here. It takes, according to the book, 22.6 times 10 to the 5th joules for every kilogram. This is how many joules it takes to boil 1 kilogram of water, which is already at 100 degrees Celsius, not to bring it up from room temperature and boil it, just to boil it. Now I can rewrite this as, I'm going to move the decimal place 1 to the left, and I'd have to pay for that with another power of 10 here. So this is 2.26 times 10 to the 6th joules per kilogram. And I'm writing it that way because this is roughly 2 megajoules per kilogram. To boil 1 kilogram of water, which is already at boiling temperature, takes 2 megajoules of energy. And I'll just quote this number again. 1 gallon of gasoline contains about 120 megajoules of energy. So 2 compared to 120, 1 gallon of gasoline could boil 60 kilograms of water. So put another way, it takes 1/60th of a gallon of gasoline just to boil 1 kilogram, which is 1 liter of water. That's kind of surprising, right? I mean, that's quite a bit of energy. If you want to boil 1 liter of water, you need 1/60th of a gallon of gasoline. So it's not cheap to boil water if you're using fossil fuels. Okay, I am just going to plug in all the numbers. I'll quote them real quick. This is the 449. Notice, oh, I'm sorry, this is the 449. The specific heat of iron is considerably lower than water, 4190 for water versus 449. We know the final temperature is 100. The iron started out way the heck up at 800. The water started at room temperature. They gave us that. And I quoted this value. So I'm going to pause, plug in all these numbers, and then we'll go back and, again, do this in a spreadsheet. Okay, I did manage to get the same answer as the solutions manual. A word of caution here. In previous problems, I had masses downstairs and upstairs, so I didn't worry about converting from grams into kilograms. Here, I wouldn't do that because you've got a latent heat downstairs. So the safe thing would be to leave everything in SI units. Also, be careful about sign. Final minus initial for the iron dropped from 800 to 100. So this temperature difference is negative 700 degrees Celsius. Negative would make it positive. So just be careful with the signs. And here's the number I got. That's in kilograms. So that would be 41.5 grams. And the problem was asking what's the fraction or percentage of water that boils. And that would just be the mass that boils compared to the total mass of water. Well, 41.5 grams were boiled compared to the original 200 milliliters, which is 200 grams. And that looks like it's about a fifth or 20%. So 41.5 divided by 200. Okay, so roughly 21% of the water boiled. That seems reasonable. It's not a very large chunk of iron. You wouldn't expect it to boil all the water. Let's do this in a spreadsheet now. Once again, I've just adapted the spreadsheet to this problem. Let's enter the values we're given. Well, we calculated using the 65 milliliters of volume for the iron. What was it? We found that the mass of the iron not originally, but just that doesn't change, 512 grams. So I'll put 0.512 kilograms. The table tells us that the specific heat is 449 joules for every kilogram for every degree Celsius, and that the temperature of the iron initially is 800. We've got 200 grams this time. I remember 200 thousandths of a kilogram, 4190. It's actually more like 4186, but we're dealing with three sig figs here. And the initial temperature of the water was room temperature, as always in these problems, it seems. Okay. The final temperature, remember, that's the one where we had to fill in the blanks. We knew that everything's going to end up at 100 degrees because we don't expect all of the water to be boiled and then get superheated. So I can calculate the heat given up by the iron. That would be mass of the iron times specific heat of the iron times the temperature difference, final minus initial. All right. I don't really care about that last decimal place, so I'm just going to decrease that, the number of decimal places shown. That's quite a bit of energy there. 161 kilojoules. That's more than one nutritional calorie. Okay, what's the heat absorbed by the water just in the process of reaching 100 degrees? Remember, there's two heats arguably absorbed by the water. First, we have to absorb enough to get up to 100 degrees, then enough to boil the amount that we calculated. So this would just be NC delta T, mass of the water times specific heat of the water times the temperature difference, final minus initial. Did I goof something? Shouldn't the heat for the iron be a negative number? I think I had the temperature difference backwards. Let me check that. C4. Yeah, I did initial minus final. Good catch, Ben. Final minus initial. The iron should be giving up energy. Okay, I'm sure some of you noticed that, and you were mocking me from the safety of your room. Okay, this is the, we can't, the idea here is not to calculate this directly because we don't actually know ahead of time how much mass of water was boiled. That's what we're trying to find. But what we do know is that these have to sum to 0. So I could just, hang on a second. Remember this condition? The sum of the 3 heats must be 0. I forgot my plus sign there. Let's solve that for the latent heat of vaporization. So over here I'll say the heat absorbed by the water for the purposes of vaporization would be the negative of heat for the iron and heat for the water in terms of raising its temperature. So we just have to sum these two and take the negative of that, and we've got the heat associated with vaporization. So over in this cell, I'll say that this heat must equal the negative of the sum of these two. And we're expecting a positive number, are we not? Yes, because the water is absorbing heat in the process of undergoing a phase change. All right, now that we know how much heat is absorbed, we can go back to this equation. And you know, maybe I should have just said Q sub L to keep the subscript simple, but I'll stick with what I've been doing. The heat absorbed by the water for the purpose of vaporization, that would be the mass that's vaporized times the latent heat of vaporization, that's an L, and I'm solving for MS. So I would just take that heat and divide by the amount of heat per kilogram. So in here I'll say this would equal that amount of heat divided by, oh, you know what, let's do an absolute cell reference. Over here, I'll do this. I'm gonna use the same font here. So the latent heat of vaporization for water. I'll just enter that value. That equals, what was it, 2.26? Or 22.6 times 10 to the 5th. All right, and now I can make an absolute cell reference. Well, since I'm not doing anything iteratively, I can just refer to the cell as normal. So equals this heat divided by the latent heat over here. And there it is, there's our 41.5 grams. Okay, so for the percent boiled, you know what, let's make things aesthetic here. Take that heat and divide it by latent heat of vaporization. Okay, so that these cells are one on top of the other. Otherwise, it's irritating to look at. I'll take the heat, or the amount of water that's actually boiled, divide that by the total mass of water, and at the end I'll multiply by 100 to convert that into a percent. And that's ugly to look at, so we'll decrease the number of, whoops, the number of digits. Good enough. Kind of nice to do things in a spreadsheet, right? I took Excel for granted for all these years. I'm so sorry, Excel. You're super useful, and I'm sure I've only begun to explore all the possibilities that you offer. Okay, that's enough for the problems in this video. 3 good calorimetry problems. Next time we'll move on to some slightly more difficult problems.